review what
That's
we
fine,
discussed.
that's fine.
Okay. So then this, we also discussed that the angular momentum is constant. Therefore, we select this. Yeah. We select the angular momentum as a z-axis. So the 3D problem also reduced to 2D problem. Then after that, we remove the prime. This is Lagrangian, right? This is not the angular momentum. This vector is angular momentum. This is Lagrangian. And from now on, we remove the prime. So now this is just consider it's a single particle problem, but the force is central force. So usually it's the function of r. Now this is in the polar matrix, right? Right? Now here we found out that this theta is cyclic because theta does not appear in the Lagrangian. So immediately know associated with this theta, we have a calculate momentum p theta, which is constant. So from here we got this theta dot, the first variable, the time dependent, the first order derivative is equal to this formula, and we call this first integral, since Lagrange equation is second order differential equation. Now we reduce. So that is for theta. Then in principle, if you do the integral, theta is function time, speed depend on this integral. So it seems like we have a solution for this formula, but the key is here. We know that r is unknown, which is a function of time. So that means even though we have this formula, but we still do not know, so what is r as function of time? This is what we are going to discuss today, and then we go to further. Okay. So to discuss this, we first, we can also, there are two ways from Lagrange equation as a function r for the general coordinates r, we can get it, or from another way, we are going to find another constant. Here, this constant is angular momentum, right? And for this system, there's another physical quantity is also constant. From there, we can also reduce the Lagrange equation from second order differential equation to the first order. So that is the goal. Now let's look. Check h, energy function, right? So remember the energy function h by definition, that we just follow this topic, right? So which definition, remember that is, we have only two variables, right? R dot and, okay, let's just use this. Plus theta dot partial theta dot, right? Minus L, right? That is Lagrange, this energy function, which defined. And then we can do R dot here, right? R dot. And this one, I didn't write down the Lagrange. So if you remember Lagrange, here, L times L, right? So that is half of, I think, m r dot square plus, I take m outside, right? Okay, outside. Dot square plus r square theta dot square. That is kinetic energy, right? Minus potential energy, which is function r. So now here, then the partial L partial r dot is m r dot, right? So now we have m r dot square, right? They have a factor. Okay, so that is this one. Second one, theta dot. Then the partial L partial theta is this one. So we have, let me just put together. Okay, theta dot, and then is m r squared theta dot, right? Is this one. And minus, okay, minus L. L here, half of, and just separate m dot squared, and minus half of m r squared theta dot squared, plus v, right? So you see the half, so now you have a half of m r dot squared plus m r squared theta dot squared plus v. What is? This is a kinetic energy, right? So that is energy, and we know we can prove because remember we said that the condition for H equal to E is, because first if, right, there's a two conditions, right? First one, R does not depend on time explicitly. Second, potential is only function R. In that case, we will have T equal T2. T naught, T1 disappear, right? And L naught is minus V naught, V. So that gave us H equal to E. Remember this? So yes, it is satisfied this. Then we can have, if you remember, H equal to L. Okay, let me just remind you, I think that equal to L2. And then if you remember, H is L2 minus L naught, right? So that is T minus plus V. That is also proved now. So yes. Now then, let's look. The dH, let's see whether H is a constant or not. Let's look this time derivative of dH is equal to minus L minus T, right? Remember this dynamic? We discussed whether it is conserved or not, and partial L partial T equal to 0, because the L does not depend on time explicitly. So we have H equal to E is constant. We have another constant, right? So we have a conserved is angular momentum, and second, the energy is conserved. Now, if this energy is conserved, so now we can have another one. Let's go back to see this. So now let's go back to here. We are going. Our goal is to find this, right? R dot. So now this one, we have the theta dot formula. So now we are going to replace. Now let's go back. So E is okay, half of m r dot square plus, okay, let me just write down here, m r square. And the theta dot is here, this one, right? Theta dot square, so that is L m r square plus V r, right? So you see, this is only function r. Theta dot or theta disappear. I have a half, right? So that is half of m r dot square. Then here, this is the false, right? So we have kind of this one, and this one has we have half of L square m r square, right? And plus V. Okay, so now this is unknown, which we are going to solve, and E is constant, so we have R dot. I think this is very easily you can find, so I just jump the intermediate step. R dot. Okay, R dot is square root 2 over m energy minus this term 2mr square and this term, right? This is the second integral. Actually, this one second. So you see here we have this. The solution for R. It is down to from second order differential equation down to the first order differential equation. So because this is dr dt, then we have a dt integral equal to, right? So here this is a dr in the determinant, and not because it's a denominator. Okay, so now, of course, here this solution is not r as function t, but the time is time as a function r in principle, right? So now, when you summarize here, so if it says from t naught to t, then the corresponding t naught is r naught to r. So therefore, finally, that is if we select t, you can move t naught here, or t naught is 0. That is this integral. E minus Q squared 2n r squared minus b. So in principle, we can get by if we have the solution, take inverse, we try to find this r as a function of time, right? So now, let me give the formula here. This is equation 1. This is equation 2. So in principle, we have the solution, or we have the formula try to solve this function of the this angle as a function of time, or r, the radius as a function of time. In principle, it is doable, but it is very difficult. You see here, first, if we really want to do this, we need to find this one, right? We found r as a function of time, we need to solve this. And from here, you see different potential. This integral, in most cases, is not easy to manage or to do it. So in principle, say, okay, we have the two formulas to solve this, the central force problem. We can find r and theta as a function of time, but it's not easy to do. So next job is, before we go to the, or instead of interest in this trajectory or the dynamics of r and theta as function of time, but we are interested in what type of motion. If the motion is like a linear motion, or trajectory is linear, or a circle, or ellipse, or the parabolic, so that is more interesting than to solve this one. So we want to understand or classify the object. So not the orbit of motion, right? So that means we are interested in find r as a function of theta. Because r as a function that gives us in the space, we can understand what kind of so that is this is x, y, right? And the column is r, is theta, right? So depending on this function r, theta, we can plot the orbit of motion of the particle. And how to obtain this? It depends on this potential. As I say here, you will see different potential, and also depends second one is the energy, initial energy and initial angular momentum. Right, so that is, even though we know the potential, but if the initial energy is different or initial angular momentum, then the trajectory or the orbit is different type. So now let's see how it works, right? How depend on this. That is our next job and the major topic today. So in order to do that, we need first introduce, we call this factorial function, potential energy. Okay, let me just come to here. But we are going to analyze, as I said, the potential is important. And another factor is this one. You can see this potential is dimensions energy, right? Joule. This one, so this turns to be another energy, potential energy we are going to. So this altogether we call the factorial potential. Okay, since that is already there, I don't need to derive this formula from Lagrange equation. We will do that in the later when we go back to analyze the. See if we need it. Okay, let's do this, since we need to introduce force also. So, okay, now we are going to introduce the factorial potential. Factitious potential. let's first from the Lagrange equation. Lagrange equations for R. We didn't do this, right? So Lagrange differential equation for R, if is d dt partial L partial R dot minus partial L partial R, right? Equal to 0. That is this. And I erased the Lagrange, right? The term. So I just give you the final since we know this. Okay. Here, that is mr dot double dot from here, and we have a minus mr theta dot square and plus partial v partial r equal to 0. Since here, partial L partial R we have a term, right? Partial L partial V. Okay, so that is equation. And now we are going to substitute this one. I think I erased, right? The theta dot from the constant angular momentum. So this one will come down to m dot, double dot, minus, this is minus, right? Minus L square of mr cube equal to minus, and move to the right hand side. So I'm going to introduce this force, right? This force is gradient of the potential with respect to R, negative gradient, right? So that is this term. Then you can see this is a function of R. Now I'm going to move this one to the right hand. So only now is, this is like Newton's second law, but this is radial. The second order derivative of radial, right? Radial part is Fr plus. Okay, we have this term. Then now we have this term. So now you can see this one. Since this is a partial V partial R, right? So that is negative partial R. This is a V here. And this one is plus L square 2mr cubed. Sorry, R squared. You see here, if I do the derivative, I have factor 2 cancelled, and then R go to cube, right? And I have minus sign. Is this? Yeah, minus sign cube, right? So this is just a positive. So you see here, there's another potential. I'm going to say give a V prime. Okay, so this V prime we introduce is V plus this term. We call it factorial potential. Potential energy. Okay, that is we introduce this the new potential, and the reason why we say the factorial potential, we know the real potential is this one. So we have additional. This is 2. So we have additional term. This is like factorial, and you know this term depends on angular momentum. If angular momentum equal to 0, there's no this contribution, right? So then for this one, and this also like if I introduce as F prime R, this is also the force which later we are going to use. So here you will have another is mr double dot is nothing but equal to F prime R. F prime R is partial the factorial potential with respect to R. So okay, this one we will keep, later we are going to use, but now let's come to see this one. The factorial energy we introduce. Now when we introduce this, now let's look at this several important information you can get from these definitions. Before that, I'm going to give you discuss velocity, since now for this central force problem, we need this correct velocity. So here, if we have a trajectory, whatever is the particle, so at this position here, this is the velocity v, right? And this, if this is r, so now this is a vr, and tangent. Okay, sorry. Yes, this is a v. So we have a v theta, which is perpendicular to the r, right? So we have this, and we have angle. Actually, I think this is better. Okay. VR. So this is V tangent, and this is a V theta. Which is the velocity project to the theta direction, and velocity project the r direction if this is too big. So no, that can form this. Right? So that is, so here we have the v square equal to r dot square plus r square theta dot square, right? Which is v r square plus v theta square if we in the polar coordinates, right? So that is definition. So then here, the radial part velocity, okay, VR is nothing but r dot, and we have it here, right? So r dot, we have the formula here, that is 2 over m energy minus L square over 2 m r square minus v. And v theta is r square theta dot square, and we have okay, so that is square. So r is r theta dot, right? V theta is r theta dot, and then we know the theta dot, so that is L m r. Theta dot is L m r square, but we have r cancel. So you can see this is a relation, and we can also get this from this kinetic energy. We know that is this E minus the real potential, right? So we have several equations here. I just give you the information, the relation here. The reason why I introduce this, come back here, we are going to discuss the orbit, right? Or classify the different orbits depending on the type of potential and initial energy and angular momentum. So when we introduce this, now we have such relation. So relations or informations. First, okay. So from the total energy, we know that is let me use this one. Half of the radial part, right? Plus the fractional potential, we have this term. This is L2mr squared plus V, right? And then, since this one is fractional potential, so I'm going to say it is a half of mr dot squared plus V fractional. V prime, right? Okay, so this means the difference between energy and the fractional potential gives us mr dot squared or half of mvr squared. Radial part, right? This one. So that means if we look this, given the potential, we look this difference give us what is the radial velocity. That's the given. So that is one information. Second one, energy minus V is total kinetic energy, which is half of the total velocity, right? So that means this difference gives us total velocity information, the difference between energy and the potential. The third one is from fractional potential. We know that is this term. Yes, good. M r squared plus V, right? So this, the first term is here. Here. that is half of mv theta squared, right? Plus v. So we have another term, difference v prime minus v. Difference between the factitious potential energy and the real potential energy is actually is this one. Or so this gives us the radial velocity. That means we are going to look the energy curve or in the plot to see three differences. This difference gives us about information radial velocity. This difference gives about information about the angular velocity or angular speed or velocity, and this difference gives us total, right? So with this information now, we can go further. Let's, as I said, this depends on different type of potential. So we are going to, I'm going to keep here since it's important. Okay, case one. We have got case one too, so let's just potential. The first case for let's see before we for force R is proportional to minus 1 over R squared. Ignore the coefficient or something. So this means the potential is minus, whatever we use K, right? We can have whatever. Yeah, that's enough. Okay, so that is we concern. Okay, so that means potential is 1 over R negative. Let's see what happens. So now we are going to plot the factitious potential as a function R. Okay, so now first let's do this. The real potential is negative, right, and decreases. So now we have a real potential. Let me just use solid line. Okay. So this one, let me just use this. This one is V. Is VR. Okay. Now, factitious potential has this term, right? This is positive. So for given L, let's assume that it is very high, right? Okay. And decay fast. So this one is L squared over 2mR squared. Then, what is V prime? V prime is this addition, right? Negative plus plus. So now, since this 1 over R decay, when go to this, when R go to smaller, is smaller than this one. This is faster, right? So when smaller R is positive V prime, and then decrease. Go to the negative, and then increase. Since this one go faster than this one, then R go to infinite, so it will slowly go to here. This is the big one, right? So I'm using black. Okay, so that is the for giving this potential. Now, for giving this potential, we will have right. Let's see the green color. Depend on initial energy, right? So suppose we have initial energy positive. I'm going to say E1. Another case is E2 is 0, just initial is 0. And E3 is negative. Here, E4 is equal to V prime minimum. So we have a prime minimums here. Prime minimum. Then we can also have a correspond to the minimum, we will have a R naught here. Right, so that is a several case. Now you can see, as I say here, depend on the different potential and also initial energy and initial angular momentum. Let's consider, assume we have a non-zero angular momentum and this curve. Then you can see the different energy, initial energy, it will give a different motion. So we're going to discuss one by one. Okay, I need that formula. I think I need only this one. This one, and this one, and this one. Okay. So now let's consider case one. Energy equal to E1. Suppose the energy is positive. So what happens? You will see here, there is a cross here, right? Then the energy equal to V prime. So we have 1, the point. Okay. How about this? So any motion below R1 exists or not? In this region, do we have any motion? See here, this one always positive, right? And this one always positive, right? Because this is a square energy. So that means, since this positive means energy is always larger than V prime. If energy is smaller than V prime, it does not allow, right? So you see here, if this R is smaller than R1, the energy is lower than V prime. So that is forbidden. Because energy is smaller than V prime. So the only thing is R, R larger or equal to R1 and smaller than infinite. That is allowed, right? Okay, now let's discuss in this energy region what happens. Let's first at R1 what happened. Let's look at R1. Look at this one. R1 is this equal to 0, right? R1 because E minus E prime equal to 0, V prime is this point. Energy just equal to V prime. So R dot is 0. So what does mean R dot is does not change R, but when R, if we say this decrease R, right? Change until here it will stop. No any more change. The only change is when you go back. So this is turning point, right? And how about in this case the theta dot at R equal to R1? How much? Is controlled by this. The difference between prime and V is this controlled by this theta, right? And this is 1 here. So that is L square over 2 M R1 square. It's not 0. And you can see at R1, you see the difference. This is V prime, right? This is a V. So very big. The difference between V prime and V, very big. It is actually is go to this is the maximum value. So you can see, if you look at this one, so you can see the difference. The difference between the V prime and V, right? So when R go to infinity, this difference becomes small and go to 0. But when R decrease. So this increase, right? When R go to R1 is biggest. So that is angular velocity is the largest, the maximum value at R1. So turn very quickly, right? So that is. Then after that, R larger than R1. Okay. So you can see in larger than R1, then you see with R increase, the difference between V prime and V is decrease. So theta dot decreases. How about R dot? R dot is the difference between energy and V prime. So initially it's 0 here, right? Energy V prime. And then we can increase R, this difference, right? Between here and here, here and here. So increase, right? But increase until to R naught, then become decrease, right? So increase for R smaller or equal to R naught, and decrease when that's 4, not 4. Then how about this when R go to infinite? When R go to infinite, you can see here this difference becomes 0. I just give you the information. The reason why, because it's term, right? And this one is E minus V prime. You just look this from the curve, you can analyze qualitatively. Then when R go to infinite, theta dot go to check out, go to infinite or go to 0. The difference is difference. So that's the difference until 0, yes. No rotation, then you go further. And how about R dot? R dot is this one. So when go to infinite, the V prime go to 0, right? So that is the only constant. That is do this way. V R is 3. Because the angular velocity disappeared. Only the radial velocity equal to the total velocity, right? And the energy is, okay. So energy is equal to m a square equal to m a r square. Okay, for this case, I just detailed analyze in different region. And later, I will just go quickly other case since just let you know how to analyze it, right? So that is case 1. And you know what is trajectory or what kind of orbital in this case. It must be open, right? It is open and here, this is R1. Go to this. Sorry, this is R1. This is R1. This is X and Y. So the particle will go from infinite and with given initial energy or kinetic energy, then when closer the kinetic energy, the radial part and angular part increase, right? From infinite and then come down to here with a turning point and then go further. The angular momentum decrease and the velocity, radial velocity increase and then decrease until to infinite line. That is hyperbolic. Followed mathematically, that is a hyperbola curve. And later we are going to summarize how. So that is open orbit. That is open. So now this is the first case we consider if initial energy is positive. Then we can analyze what happened. Now let's consider the second case. Case 2, energy equal to E2, just equal to 0. So I still use this curve here, and if this one, now this is R1, right? We still have this case. let me remove erase this part. Is okay? Okay. So now we consider case 2. I use the same figure, so at the same time. Okay. So that is R1 right here. This because this is this position energy equal to this V prime. And then again, before the R1, there's no, it's forbidden, right? So then I will not discuss this part. Let's discuss. So this is a turning point. Where's the turning point? Is R1. And the R1, at R1, we have R dot is equal to 0, theta dot equal to the theta dot maximum. Same thing, right? You can see here the difference is the difference between V prime and V. So you see the theta dot is when R close to R1 increase, right? So that go to maximum. Then the R1, then R larger than R1. So theta dot again decreases. And the R dot same thing, right? R dot here, first increase and then decrease. Increase for when R small than R not, and decrease when R larger than R not. And then again, when R go to infinite, so theta dot go to 0, and R dot, okay, R dot is equal to V, R is equal to V. But V is, in this case, since n is 0, right? So you see when R go to infinite, the difference between energy and the V prime is also go to 0. That's the difference. So in this case, initial energy is positive, then even go to infinite, still have a non-zero velocity. But for if initial is 0, then go to infinite, both the angular momentum, angular velocity and the radial velocity all go to 0. So, orbit. Again, it's open, since we know it will go infinite, right? So that's open. And if we plot here, let's say this is R1, but here, you see this is no flight. Okay, so here, like this is a parabolic, or parabola. Okay, now let me use this part. So now case 3, energy is negative, but still not higher than the minimum, right? So that is this case E3. So in this case, now you can see here we have a 2 point. And these 2 points, energy equal to V prime, right? So now we have R1, R2. And how about this? Before smaller than R1 and larger than R2 is forbidden, right? Since larger than R2, the energy is lower than the V prime. So R is limited. Cannot go over. So that immediately you know that's the closed orbit, not open. Right? If open, R can go to infinite. But in this case, R is within the range here. Then R1, both cases, R1, R2 are turning point. So we have 2 turning points. previously we have only one. So now we have two terminals. That makes sense if they're close. So we go to somewhere and back and go to another one back, right? That makes it close. So that is the case. And then again, you can discuss the radial velocity at this case, right? So if a turning point, then we immediately know at this 2.0, right? That is turning point. And now let me ask theta dot. Let me say theta dot 1. Oh, okay, let's just say at R1, how much is we go to the maximum value, right? Because again, you see, you see the difference. So the difference, the angular momentum is different between the V prime and V, and the R1 is big, the R2 is very small. So, and theta dot R2 is minimum. You can see here. And this is also makes sense since they are equal to L, I think equal to L MR1 square, right? I need to remember. I just erase that one. Velocity is LMR. LMR2, R1, R2. So that only depends on R1, R2, and R1 is smaller than R2, so the angular velocity is larger than R2. Then that is, and then the others you can discuss, for example, between R1 and R2, then you have the like oscillate here. Between R1 and R2, the kinetic energy when from R1 increase, you see the kinetic increase because as kinetic energy, so this is the energy difference that gives kinetic energy or radial energy, sorry, radial part, and then decrease, 0, and increase, and decrease, right? Angular velocity increase, but decrease. So that is what happened here. So something like you can discuss like this. I think, yeah, same thing like this. There's no this term, right? So now the orbit. Immediately got this orbit. The orbit, in this case, be close. Orbit, right? And close orbit here, in principle, we have this, we know the ellipse. So now let's consider the case in general is we go to the ellipse orbital. And here, this is center, so this is R1, this is R2. Okay? From center to this point is R1, from center to this point is R2. So that's the turning point. And then if we keep this like counterclockwise, you will see here, this is in this case, this velocity at this point, only theta, right? Because the radial part is 0. Similar thing here, right? And this is a theta at R1, and the V here, V velocity is equal to the angular velocity at R2, right? So, any case, if you have this, in any case, velocity V here, and you have R, VR, and here, so this has to be this way, right? And theta. We don't want to make this velocity. Oh, yes, direction opposite. So here, this is the VR, and then this is the theta. In any case, but there's also possible another case which follow this motion with two turning points, but it is not close. It is bounded. it is also possible like this. Now I'm going to plot. So this is R1, and we have a bigger circle. This is R2. Let me use color. So here, this one initially, okay, that is this one. So here, suppose we have go to R2 and come back here, right? Here. And wait a moment. I think I made a mistake here. This is two center. This is R1. Okay, so we have always have orbit is too much. And then come back to here. So you see here, this is always, you have a small circle inside, which is keep R1, and a larger circle outside. So, but they will not go back to the same orbit. They will try to, when they come to here, they try to go to another, turn to another orbit. But always keep between R1 and R2, and always has the turning point here. That is so-called the bounded, but not close. Bounded orbit. Okay. Now we go to the next, the case 4. Case 4 is simple, so energy just equal to E4, which is minimum V prime. If minimum here, there's only this point. Because when they are, this is R naught, right? When R larger than or smaller than R naught, in all cases the energy is lower than the V prime, so that is forbidden. So the only allowed is R always equal to R naught, not any other. So this is immediately we know that is circle, right? Circle, orbital is circle. And in this case, definitely always equal to 0. R will not change. They keep the circle, right? So then there's only this one, and this one is L M R naught, right? It's a constant. Okay, and in this case, can I erase this part? Okay. No, this is the textbook we have. So, okay. Now, this case, you see this V prime go to minimum, and if you remember, F prime is negative V prime partial R partial raised, right? So that is in this case 0, right? This circle, since there's a minimum. So that is means this is just at the minimum here. So we have this one, and then this one, not, right? So in this case, this is definitely also a constant, since R will not change. Then, if you remember, we have, I just erased, so then Fr, if you remember F prime, that is equal to Fr plus L MRQ, right? I just want to do this. So we have this force, the real force is negative square of 2mR naught Q. And do you know this? This one is equal to negative mR naught theta dot square. So this one is a centripetal force. Centripetal force. And that makes sense. So when we do the circle, it's R naught. Right, so that is a force here. The force, this one is F R, right? R naught. And that is balanced with another centripetal force here, which is the opposite direction at equilibrium, right? So that is the situation in this circle. Okay, so if we summarize a little bit, you can see here, depending on the energy, as I mentioned, even though for getting same potential, but between the initial energy, it will have either open, for this two cases, open orbit, for this case, closed orbit, this is an ellipse or kind of bounded orbit, this one is totally circle. So that means if we know the potential, even without solve any details, we already know what kind of orbit here by this analysis. Now, let's go to another one. Another case, C. I will ask you think about this. I just discussed one case. The other case, you can think about this. Okay, 2. For the force is proportional to 1 over r to the fourth power. So the potential R is whatever you can use equal is okay. Q. Okay. Decay very fast. So now let's see in this case, what kind of motion? R. Let's first plot this one. So that is decay very fast. And then when the R go to infinity very close, but quickly, but when R go to 0, this is very deep, right? So very deep. Compared with the V1 over R. And then this one is still same, right? So this one decay is slower. Oh, I use colors to do that part. Okay, so that is still square. Then the factorial potential energy is the difference of this. Then you can see here, when R go to 0, this one is negative, much more than this one. So this V prime is like this. Right, that is V prime. So now this is a V. This is a VR. And this is okay. We did that one, so that is V prime. V prime. Then we do the same analysis, depending on the initial energy, right? So the initial energy may be like, I'm going to say this is E1. This is E2. Okay, so this E2 is just this V prime maximum. It's still minimum. Here we have a maximum. Okay. And then the next one is, let's use this below the maximum, but still positive, E3. I think that's enough. Maybe E4 is actually, okay. E4 equal to 0. Okay, so we have this 4 case. Now for this 4 case, I want you to think about, or you think yourself. Think. dot cases E equal to E1, E2, and E4. I'm going to only discuss this case, E3. Since E3 is more complicated than others, and if you know E3, I think you can use the same idea to analyze other cases. So now let's consider E4. Sorry, E3. Now E3, you can see we have a two turning point here, right? I'm going to say R2, R1. Then I'm going to give a three region. So this is region 1, region 2, region 3. So now let's consider case energy equal to E3. So we have a three region. 1 is 0, R1, and 2 is R1, R2, 3, R2, infinity. So now, let's first forbidden area or region, which one? Forbidden region, where the energy is lower than the V prime. 1, 2, 3, which one? See here, this is V prime, right? Black. This green color is the E3. So where this area, the E3 energy is lower than V prime, right? So forbidden region is region 2. That makes sense? Okay, so we will now discuss. Then now we discuss two regions. First, region 1. In region 1, R is in this limited this, right? So that's this area. Okay, from here to here. So the motion is between 0 and R1. But 0 is not turning point. Turning points be also always energy equal to V prime, so the R dot is 0, right? Here, R dot is not 0. Because this energy, this is V prime, so you see the difference. Or proportional. Right? Always consider this proportional. The difference. Right, so we already, the formula I gave you, right? Remember that this radial velocity or kinetic energy is equal to the difference between energy and V prime. So when energy is always higher than V prime, so the difference even up, you see this go to infinite. So R dot, so at, then R dot increase when R go to 0, right? How about the theta dot? Theta dot proportional to the V prime minus V, right? So V prime, this is V prime, this is V. And but you know the if you remember, this is this term, right? So what will happen? We will also increase when R go to 0, right? Because in the denominator. So you can imagine when the R, the particle from R1 and go close to R and very fast, the speed, the radius fast, and also the angular rotation is very fast. And after that, go through that and then come back, increase the radial and the velocity, radial velocity and this angular velocity all decrease. So turning point, we have a turning point, right? R equal to R1, right? Since here R1 dot is 0, because E minus V prime is equal to 0. Is this point. Okay, and what is trajectory of the orbit? I want you to think about orbital. What is orbit? What kind of orbital or orbit? Challenge to consider with this information. Think about it. It is bounded, right? Because only between 0 and R1. With this ellipse, if ellipse we have two turning points, but this only have one turning point. It will be a challenge. Think about it. Okay, now we consider this is for region 1, right? So discuss region 2, region 3. Region 3 is R2. It's this here. It's from here to infinite. So definitely immediately you know the orbit is be open, right? Since we know it's allowed to go to infinite. When you go to infinite, energy is always higher than V prime. Since V prime will go to 0, so that is kind of a parabolic. Hyperbolic, sorry. Because its energy is not go to 0. So the hyperbolic, parabola. Okay. So in this case, again, at R equal to R2, it is turning point. Since R2 dot is 0, and here we have this one. Then how about the theta dot? Theta dot R2 is a difference, if you're not 0, right? Because that's the difference between the V prime and V. So this is a difference here. Non-zero. It will also maximum value, since you can see here. This is the difference here, right? We increase R, the difference is smaller, and go to 0. So that's the maximum value. And that is L M R2, right? At this value. And now when R go to infinite, since there's no minimum, that doesn't, because R now is in the forbidden region, right? So we not have no information to discount this one. Only for infinite. So the R dot infinite, you see R dot is the difference between energy and the here, right? Energy and the V prime. So that is smaller 0 and increase until go to constant, right? So the R dot increase until V R equal to V, and that is equal to the square root of M2 potential 0, right? In that case, potential is already 0. So that is, and the theta dot decrease and go to 0. Since theta dot is different between V prime and V, all both go to 0, so that go to 0. Then the orbit again is like this. Hyperbola. This is R2. And this is turning point. Any question to here? I think go a little quick. So, okay. Finish this potential. Now we go to another example. Is potential proportion to R, not this running R. Let's consider this case. Number 3. Like a string, right? So for R hook type. Force. So the force Fr is minus Kr and Vr half of Kr squared, right? So now I see the potential is positive. Now let's plot what kind of the curve, the relation between energy, potential, and the factorial potential. So now here, this is I'm going to use blue again. So here, that is this one, right? Increase. And this is this one. And then, how about this another term? This one, this angular momentum is still decreased. So that one will. Then now we have this factorial potential by the addition of these two. So we'll have here, so that is something like this. Right? That is the V prime. Now let's look at, in this case, how about the energy? The possible energy. Since the possible energy cannot go down, right? Here it's forbidden, since energy always be higher than V prime, so that is only this case. Only two cases, right? E1, E2 equal to V prime minimum. Only these two, right? So now let's discuss case 1. And okay, so suppose you have a minimum here, R0. Case 1, energy equal to E1, which is positive. Then you can see here we have a two turning point, R1, R2, right? Turning points, R1, R2. And then this, the turning points, we know R1 dot equal to 0, and R2 dot is also equal to 0, because in this position, energy equal to the prime. So now we know this definitely is a closed or bounded orbit, right? Because it's bounded between R1 and R2. And in this case, so how about theta dot R1? Now again, you can see theta dot is the difference between V prime and V, right? So R1 is bigger, R2 is smaller, right? So you see the difference increase, decrease, 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 right? So it is also the maximum value, which is L and R1, right? And theta 2 R2, which is actually smaller, minimum, is L and R2. So that is a turning point. We know the radial velocity is equal to 0 because turning, and then we have definitely have an angular momentum velocity. So that gives us this picture. And above between these two, you will see between these two the radial energy is different between energy and the factorial. So that increase, increase, increase to here and decrease, 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 right? So R1, R2, okay, this one increase for again smaller than R0 and decrease R0 right? Theta dot always decrease. Okay, you can also discuss energy. So, which I think I leave that for you. That is, with energy is associated with this, the velocity, right? So, see, okay, orbit. Orbit is what kind of orbit? Same thing here, right? Either closed ellipse or like this bounded, as I did before. Okay, it already time, so okay. I will draw and plot this one next Tuesday to continue. Then we go to discuss this circle. And in this case, we also discuss if angular momentum is 0, must be oscillation, simple harmonic oscillation, right? Okay. So I want you to play yourself or try to understand this. Then any case give you arbitrary potential. You need you know how to analyze what kind of object yourself. I have 3 types of potential here, right? So if a change, and whether you can know how to discuss this for giving initial energy, how to discuss what kind of possible orbit or what kind of motion they will have. We have a turning point, which area is forbidden, so all are can discuss. And if open at the infinite, it is stopped there without any energy or still keep move, will not come by, we have energy. Okay, let's see, I have yours, I have yours. This is yours, right? Okay, okay, thank you. All right.